Okay, so we started talking about probability today in class. So first we look at probability as a whole. Okay? And then if you look here, you see the definition for experimental probability says the number of times the event occurs out of the number of trials. And those are a concrete number. Like you have results of an experiment, and you look at those exact values. And then we're going to talk later about theoretical probability, where we have to be able to analyze the situation and count the number of possibilities. So, for example, it says you observe 119 animals at the zoo. 19 of them have wings. What is the experimental probability that an animal at the zoo has wings? So, again, for probability, we want to put the number of times our event occurred. So here the event is having wings, which is 19 of the animals, out of the total, which was 119. Then you would reduce it if possible. On a multiple choice test, each item has 3 choices, but only one choice is correct. How can you simulate guessing the answers? What is the probability that you will pass the test by guessing at least 5 of 10 answers correctly according to your simulation? So what we're going to do right now is we're going to use our calculator to do a simulation, and I'm going to show you how to do that. We'll do one together, and we'll use our simulation to answer this question, but you could always do your own. Okay, so on your calculator, remember our problem said it was multiple choice with 3 answers. So I often pick your guys' groups like this in school and stuff. If you go to math, and you go to probability, the same place where we get our permutations, combinations, and factorials, there is a random integer if you choose choice 5. Then you want to tell it what to choose the random integers between. So you want to say between 1 and 3. That's how we're going to simulate it. That's because we have 3 choices in this problem. Then I'm going to tell it how many questions are on the test, so to speak. So if we look back at our example, 5 of the 10 answers correct. So there's 10 questions on the test. So what the calculator is going to do for me is it's going to generate a list of random numbers, a list that's 10 numbers long, and it's only going to include numbers 1 through 3. So I'll go ahead and press enter. And so we'll see my first list right here, and it's 3, 3, 1, 2, 2, 3, 1. I can't see the rest of it. Okay, I think I figured out what was done. I am going to quit this stuff. That's fully messed up. Okay. All right, so now that I got my calculator clear, let's try this again. So the buttons were right. We just can't arrow out of it once we have the answer. And what I mean by that is go to math, probability, choose choice 5. And again, we want numbers from 1 to 3, and we want 10 of the numbers. Press enter and don't press anything else. So it generated a list, and right now if we arrow to the right and to the left, we can see the entire list. So I'm not going to push up, down, anything else till I've looked at this entire list. The question was, if we look back at it, what is the probability that you will pass the test by guessing at least 5 of the 10 answers correct according to your simulation? So if we're going to get the question right by guessing at least 5 of the 10 answers correctly, we're going to assume 1 means a correct answer. And so we're going to look for items in our simulation where we have 5 or more correct answers out of the 10 numbers listed. So there's 3 ones, 4 ones, and that's it. So that one didn't work. So I'm going to do again, 1, 2, 3, 4, 5. That one might have more ones, but it has at least 50%, so there's 1 so far. I'm going to do it again, and I'm going to do this with the simulation a different amount of times. Okay? We chose this simulation if we look back at the problem. So our simulation was built this way, and that's how you would explain the first answer. What's the probability you will pass the test by guessing at least 5 of the 10 answers correct? We have to finish our simulation. So we're going to look at 10 different outcomes and see what we get and then compare them. So in the second outcome, we had enough to get 50%. I'm going to press enter. 1, 2, I see 3 ones, 4, and that's it. So that one's going to be a no. And then in my next outcome, 1, 2, 3, 4, I see right away. See if there's another one in there, so it's at least 50. There is, so that's going to be yes. Press enter. I see 1, 2, 3 right away, 4, 5. So again, that's going to be yes for at least 5 correct. I'm going to press enter. I see 1. Nope. So far I've done 6 of my 10 simulations. 3 of them have been yes and 3 of them have been no. There's number 7. I see 2 ones, and that's it. So that's not enough to say 5 or better that were correct. Simulation number 8. 1, 2. And that's it. So again, that's no. Simulation number 9. There's not even enough spots there left, so that's no. And then my last one, because I'm only doing 10, I see 1, 2, 3 ones, 4, 5. So that fits yes. All right, so when you explain how you set up the simulation, you would explain that you use the random number generator on the calculator. Okay. What is the probability you will pass the test by guessing at least 5 of the 10 answers? So according to our information and our data, we had 10 trials, so that's our total number of simulations. And then we had 4 times that 5 or more were correct. So we would say the probability is 40% that you would get at least 5 of 10 answers correct. But again, this is not theoretical. This is strictly experimental based on our simulation. So what you should get out of this is how you could set up a simulation using your calculator, and you can ask questions about it tomorrow, and then how to read the data from that. Most of the probability we're going to be dealing with is theoretical probability. So here are some notes about some notation that you might see in some words that you might hear. So the definition of probability that we talked about in class, the number of ways to get a specific event over the total number of ways possible. We often use this to mean probability of A, where A is a certain event. Okay? If the probability is equal to 0, it means the event cannot happen. If it's equal to 1, it means it's 100% chance or completely certain that it's going to happen. And it has to be between 0 and 1 because you can't have a negative number of ways something is going to happen. And the denominator will always be the larger number, or they would be equal, because you can't have more ways of getting something specific than the total number of ways possible. Okay? If you see this little bar over the A, it's an indication of meaning the probability that an event will not happen. If you can calculate that probability on your own, that's fine. But if not, if you can figure out the probability the event will happen, you can do 1 minus that to get the probability that that event will not happen. Okay? I just wanted to compare the word probability with the word odds, because you hear that in the same context. But odds compares success to failure. So the total is those two things combined together rather than putting the total actually in the fraction. Okay? All right. So now let's look at some probability problems. What is the theoretical probability of each event? Getting a number less than 3 on one roll of a fair number cube. Number cube is like a die. Okay? It has 6 sides. The numbers 1 through 6 on each side. So getting a number less than 3 would mean that success would be considered if you rolled a 1 or a 2. Okay? And since there's only 6 numbers on the die in total, there are 6 possibilities, and 2 of them would be successful. So our probability is 2 out of 6, which reduces to be 1/3. Getting a sum that is a multiple of 4 on one roll of 2 fair number cubes. So we're going to look at a chart more extensively in class. Okay? But basically, the first die number 1, you can get any number 1 through 6. And you can do the same on another. And then you can see what the sums would be. Here the sum would be 2. This would be 3, 4, 5, 6, 7. Okay. And you can create this entire chart if you want to count the number of possibilities, and then we'll talk about how you could see it other ways later. Okay. So now to get the sum that is a multiple of 4, okay, that would mean all the 4s would count. Okay. 4 times 2 is 8, so all the 8s would count. And 4 times 3 is 12. So you see there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different ways that outcome could happen. So 9 is the number of successes out of 36 possibilities total that we have filled into our chart, which reduces to 1/4 or 25%. Okay. All right, what is the theoretical probability of being dealt exactly 3/8 in a 5-card hand from a standard 52-card deck? So if you guys don't know about decks of cards, they go, 2, 3, 4, all back, the queen, the king, and the ace. Okay? And these cards exist, I'll just use my scribble here to make the different suits, in 4 different suits. Hearts, diamonds, clubs, and spades. Okay? And then those come in 2 different colors. Okay? So the hearts and the diamonds are red, and the spades and the clubs are black. Okay? So when they talk about decks of cards, there's 52 because if you count right here, there are 13 different types of cards, and they come in 4 different suits. So 13 times 4 is 52. Okay? So we're getting a 5-card hand. So we're choosing any 5 cards from this deck. But to get exactly 3/8 means we are going to get 3 cards that are 8s. And then we're going to get 2 other cards that are specifically not 8s. It doesn't matter what they are. They didn't put a parameter on that. But we can only get exactly 3/8. Okay? Now we're counting choosing groups of cards now and not individual cards. So since this is a group and order doesn't matter, we're going to use a combination. Okay? We're going to do separate combination for each of these because this one is picking from 8s and this is picking from things that are not 8s. So in our deck of cards, wherever the 8 is, there would be 4 of them, 1 of each different type of suit. So there are 4 8s total, and I'm choosing 3 of them. Then for the other 2 cards in my hand, again, order doesn't matter, so it's a choice. Okay? I'm choosing 2 cards from anything that's not an 8. So basically anything except for those 4 cards. So remember, there were 52 cards in our deck in total, and we're not including the 4 8s. So that would leave 48. So 48, choose 2. And then I'm going to multiply those together because, like the trees that we've been drawing and stuff like that, every choice from one can be paired up with any choice of another, giving us lots of choices. So then I'll go ahead and go on your calculator and do 4C3 times 48 C2. So this comes out to be 4,512. Now, this is the event I wanted to happen. This is the success, okay? But that does not count for the total, okay? The total is basically going to consist of any 5-card hand, because that was I was counting. I'm going to be dealt a 5-card hand. So I need the total number of ways to be dealt a 5-card hand, and then the number of ways to be dealt the hand I want, which is 3/8 and 2 of any other card. That was calculated here. So the total is that I am choosing, because again, order doesn't matter, from a 52 deck of cards, 5 cards. So I'm going to go ahead and put this in. And this is $2,598,960. So the probability is going to look something like this. My successes over my total, and I know these are large numbers. I can see that they're both even though, so I'll try to reduce it a little bit. They're both divisible by 4, so when I divide by 4, here's what I get. And then you can see they're still divisible by at least an even number. So again, they're both divisible by 4. 1, 6, 2, 4, 3, 5. Obviously, you guys can do this faster by yourself, without writing it out. Okay, but those aren't going to have any common factors, and so that would be my final probability. 282 out of 162,435. Okay? And again, we had to use combinations here because we needed to count the number of groups. And we had to split into 2 combinations here because the entire 5-card group consisted of smaller groups that could be paired together. Okay? All right, the last thing we're going to look at is we're going to look at a geometric probability example. So a carnival game consists of throwing darts at a circular board as shown. What is the geometric probability that a dart thrown at random will hit the shaded circle? So here's the shaded circle. Okay. And so we want success, which would be the shaded area. Oops. Out of our total area. Okay. And so we're considering this our total area right here, that the target is this large circle. I know the picture is a little hard to tell because I cut and I pasted it, but so the larger circle is the whole area, and we want to hit the inner circle of the shaded area. Okay. Now, the way to compare these is area. So the total amount of area we're looking at is going to be area of a circle whose radius is 8, because it's a combination of the 3 and the 5 together. And the shaded area is going to be the area of a circle whose radius is 3. Okay? So remember that area for a circle is pi r squared. So for the radius of 3, it's going to be 3 squared times pi, and for 8, a squared times pi. The pi's will cancel, and we have 9 over 64. And so that is going to be the probability that we're going to hit that shaded area if it's thrown at random. Okay? All right, so when you come to school tomorrow, be ready to ask questions. We're going to try some problems in class, and then you're going to get to work on some homework problems as well.